In this section, I'm going to be talking about the wave nature of light. Specifically, I'm going to be talking about electromagnetic radiation. Now, electromagnetic radiation sounds like something that's very foreign, but in fact, a lot of what we deal with in our everyday lives is electromagnetic radiation. So, for example, when you listen to the radio, that is electromagnetic radiation. Whenever you microwave your food, whenever you see anything, all the gorgeous colors that you see, that is electromagnetic radiation. Other ones, when you break your arm, X-rays. So what this is showing you right now, what this diagram shows you, is all of the different types of electromagnetic radiation. Also, what you should notice is two different measurements that are involved, wavelength and frequency. I'm going to go over those in 1 second, but what you should notice is that radio waves have the largest wavelength, right, 10 to the third meters, while gamma rays have the shortest wavelength. Interestingly, frequency is the exact opposite. So radio waves have the shortest frequency, while gamma rays have the largest frequency. And we're going to talk about what each of those two measurements represent. But just keep in mind as we go through that wavelength and frequency are inversely related, meaning when one increases, the other decreases. All types of electromagnetic radiation, they move at the same speed. They move at 3.00 times 10 to the 8th meters per second. That is the speed of light. Here I have a diagram representing wavelength. As you notice, wavelength is the distance between two peaks. Those are called crests. It also can be the distance between two troughs, the bottom parts of the waves, but typically we define it as the distance between two peaks. So if you notice the difference between A and B, A has longer wavelengths than B does. Another term that we're going to be talking about, which I just referenced to in the previous slide, is frequency. Frequency is the number of complete wavelengths that pass a given point each second. So the interesting thing is frequency is not the same thing as time. In fact, they're the reciprocals of each other. So frequency, rather than saying how much time does it take for one wavelength to pass, frequency is saying how many wavelengths pass in 1 second. The formula for relating frequency and wavelength is c, which is the speed of light, equals the wavelength, this is called lambda, times nu, which is the frequency. So c is the speed of light is 3.00 times 10 to the 8th. Since it's speed, the units for speed are meters per second. Okay. This is the wavelength, and since we're talking about length, the units for this are going to be in meters. Notice the reason why it's meters is because the speed of light, I'm going to just write S-O-L, speed of light is meters per second. So since the units for speed of light is meters per second, the units for wavelength must be meters. Frequency tells us the number of cycles per second, and therefore the units aren't seconds, it's the reciprocal of seconds, which is seconds to the -1, because that's the same thing as saying 1 over seconds. The other unit that's frequently used for frequency is hertz. Okay, so based on this problem, it tells you the wavelength, which is 0.032 meters, and it asks for the frequency. Well, I know the speed of light, that's 3.00 times 10 to the 8th meters per second. I know the wavelength, which is 0.032 meters. Notice how I'm including all of my units for my problem. And I'm going to multiply that by my frequency. So to solve for frequency, I need to divide both sides by 0.032. And what I get is 9.375 times 10 to the 9th, either hertz or seconds to the -1. I'm going to write hertz right now. The last thing I got to do, I need to round. 3.00 has 3 sig figs. This only has 2 significant figures. Therefore, my final answer needs 2 significant figures. So it's going to be 9.4 times 10 to the 9th hertz. And that is my final answer. Notice, guys, when you're doing problems, don't let the fact that wavelength, if it's not in meters, make sure it's in meters. Don't let that mess you up. Also for frequency, make sure it's either in hertz or seconds to the -1. The next section talks about quantized energy and photons, so we are going to need to get some definitions out of the way. Before we get started, though, I wanted to talk about relating energy to frequency. So this formula right here, E equals h times your frequency. E is energy, h is Planck's constant, which is 6.626 times 10 to the -34th joules times seconds, and we'll work with that when we start doing some problems. And frequency. We have learned already how to relate frequency and wavelength with the speed of light equals frequency times your wavelength. In this problem, we have your energy equals Planck's constant times frequency. So this equation is allowing us to relate frequency and energy. So energy is here. The units for energy are joules. Then we've got frequency here. Remember, the units for frequency are seconds to the -1, or hertz, or 1/seconds. So in order for us to get joules for the units for energy, the units for Planck's constant must be joules times seconds. And Planck's constant is 6.626 times 10 to the -34th. The units are joules times seconds, because then if you multiply joules times seconds by 1/seconds, the seconds will cancel and you end up with just joules. So in this problem, it's asking you to calculate the energy of a photon. It tells you that the frequency is 2.68 times 10 to the 6th hertz. Remember, that's the same thing as saying seconds to the -1. So I'm searching for my energy. I need to calculate that. So Planck's constant is 6.626 times 10 to the -34th. Remember, your units are joules times seconds. Then you're going to multiply that by the frequency, which is 2.68 times 10 to the 6th. Your units are hertz. So when I multiply that out, I get 1.775768 times 10 to the -27th joules. Remember, because the seconds and the hertz, which is the same thing as saying 1/seconds, cancel. However, because I want 4 significant figures from here, this is 4 sig figs, and I want only 3 here, my final answer is going to be 1.78, because the 7 rounds up, times 10 to the -27th, and my units are joules. And that's it. When we're talking about quantized energy, what we're talking about is the fact that matter can either emit, so release, or absorb energy, but it only does that in whole number multiples, meaning the energy is either h times your frequency, or 2 times your energy, 2 times that energy, or 3 times that energy. There's not a continuum. It's very specific amounts of energy. Those allowed energies, those specific energies, those we refer to as quantized. Okay? They can only be specific quantities, therefore energy is quantized. Now, this seems really weird, but an analogy that's often used is stairs. You can't step in between 2 stairs. The same thing applies with energy. You can't have an energy between 2 allowed quantized energies. It's either one or the other. You don't have a ramp, you have stairs, very specific allowed energies. Einstein expanded upon Planck's theory with the photoelectric effect. In the photoelectric effect, he noted that light requires a minimum frequency in order to remove electrons from a piece of metal. And you can see that here. Energy goes in, it hits the metal. If it has enough energy, then electrons are released. He went further, though, to note that the energy is actually in the form of tiny energy packets, and he called those tiny energy packets photons. He also noted that the energy of those photons equals Planck's constant times the frequency of those photons. And finally, he noted that in order for the photons to emit electrons, in order for them to hit the metal and allow electrons to be emitted, the photons required a minimum energy in order to overcome the attraction that the electrons had for the metal. If those photons had enough energy, then the electrons would be released, and that can actually be measured by the current indicator, as you can see in the diagram off to the side. The next thing that I'm going to talk about in section 6.3 is line spectra and the Bohr model. Now, a spectrum is produced when radiation is separated into its component wavelengths. There are two different types of spectrum that we're going to be talking about. The first is a continuous spectrum. A continuous spectrum is the spectrum that consists of a continuous range of colors. And so what happens is if you have light and have some sort of prism that can separate out all the wavelengths, a continuous spectrum has all of the different colors. One example of this that you experience on a daily basis is a rainbow. So the light, the sunlight, provides all of the different wavelengths. When it's separated out by a prism, you have this continuous range of colors. That is a continuous spectrum. The other type of spectrum is a line spectrum. In a line spectrum, when light is emitted by a specific gas, you will not have a continuous spectrum. Instead, you're going to have individual colored lines, and each of those lines has a specific wavelength. So if you notice right here, the top one is the line spectrum of hydrogen. You've got very specific wavelengths, as can be seen below. It's measured in nanometers. When these are combined together, that's the light that you see when you excite a specific gas. So neon has a greater number of line spectra, but again, it's not continuous. They are very specific wavelengths. The first model that we're going to talk about in order to relate the atomic structure, what we studied in the last unit, to electrons is the Bohr model. There are two main points that Bohr made in his model that we will continue to use, even though as we continue on with this unit and future units, we'll learn that his model is extremely limited. The first is that electrons exist only in discrete energy levels, and we call these quantum numbers. So as you can see in this diagram below, you've got specific little rings. Those are quantum numbers. Now, this is not how electrons actually exist in the atom. However, it is nice to see how you have three different quantum energy levels. The first one, the one closest to the nucleus, that would be n equals 1, then n equals 2, and n equals 3. The second point that he made, that is important for us as we continue on with this concept, is that energy is involved in the transition of an electron from one level to another. So in order for an electron to jump from one energy level to another, if it's jumping to a higher energy level, it's going to have to absorb energy in order to do that. If it jumps down energy levels, so from let's say n equals 2 to n equals 1, it's actually going to release energy. Okay? So you can see this right here. If you're going from n equals 1 to n equals 2, that transition from a low energy level to a higher energy level requires energy, so energy has to be absorbed. If you're going from n equals 2 to n equals 1, that requires energy to be released since you're moving from a higher energy level to a lower one. Notice that we're continuing with this concept of specific allowed energy levels, right? The concept of energy being quantized, since you have n equals 1, n equals 2, n equals 3, n equals 4, and etc. Notice you don't have any energy levels that are in between n equals 1 and n equals 2. Energy is quantized. It's very specific amounts of